Alright. Time. So, what do I have here? What do I have here? Okay. So earlier this week, I just go over, like, review the whole process that I went through. Earlier this week, I started with the problem of a cube, some kind of mass, with a thruster stuck to the bottom of it, oriented against gravity, such that if we fire the thruster, it should cancel out gravity, and if we have the right magnitude on our thrust, I think this one's like 32 with one thruster on it. What we would get is a hovering cube. Okay, yeah, that's pretty close. And then I was like, okay, well, if the cube is tilted a little bit the wrong way, less of the thrust is going down against gravity, and in fact, some of it is going to the side. That's actually like, that's, there we go. Look at that. That's a good demonstration of that. If we do 45 degrees, we'll get even better. It'll go off to the right and it'll descend at the same time. Because it's just not countering gravity anymore, like it is when it's upright. So then I was like, okay, so Wiremod allows us to create thrusters with varying magnitudes. So I'm gonna remove this thruster. So this thruster, which is a lot better, and it's got a force multiplier of 1. And I'm gonna link it to a lever, which is a really cool and relatively new addition to Wiremod. Where did it go? It wasn't around when I was originally messing around with Wiremod. I've been doing this for a long time, and it's been a long time. So this is all really exciting to get back into. Where is the lever? Input. I saw it earlier. Lever, there we go. Okay. And so what I'm gonna do with this is the lever will output some value between 0 and 40. And the thruster's thrust will scale accordingly. So that's at 40, and this is at 0. So that allows us to think, okay, well, if we got ourselves a nice 45-degree angle, 32 on each, which was enough to balance it when it was facing straight up, is going to be too much. It's going to be the square root of 2 times too much, I believe. So if we divide the number by square root of 2, which, oh boy, all right, let's do this. It's gonna be something like, I'm gonna say it's gonna be like 20, 21 and a half or something, 32. Oh, wow, I didn't like that. Okay, so you can't see this right now, but I'm messing with the calculator. Hold on, let me see if I can show you this. Bam. Oh, it did it. Okay, excellent. So we're just gonna clear all of that, and then we're gonna 32 divided by squares the square root. I don't know how to do square root. Oh, okay. Q. It's. Damn it. Part of the fun of live streaming is just fucking around for a while, which you can't really just do on long ass video. Anyway. 1 second. I want to find this out. I have a calculator in my bag. $32 divided by the square root of 2 is, oh yeah, 22.6. 22.63. So if we set the thrust on each thruster to 22.63, it should be about right. In fact, I think it might be a bit low because, as we discovered last time, the thrusters add weight and thus downward force from gravity to our object. But let's see how close this is. Pretty close. Pretty close. A little bit low. I'm going to say if we make it 22.75, we'll be pretty close to on the money. I got my other model working pretty exactly, so that's really close. And of course, if it tilts to one side, it drifts, and if it tilts this way, it drifts like even more. And so I didn't bother really to figure out what the what it would be if it was balanced perfectly on its corner, like what that magnitude would be. I think maybe square root of 3, so 32 divided by the square root of 3. But don't quote me on that right now. So then I was like, okay, so what needs to happen internally in the thruster logic in order for the force to always be pointing upright? And so in this simple example, what needs to happen is that the thruster pointing up needs to be on, and this one needs to be completely off. And then as the thing rotates around, okay, well, 1 second. Let me just add more thrusters. I think you can hopefully see that. I guess that was really pointless, huh? Downward thruster needs to be all the way on, and then as it moves around the circle, it's steadily less until it hits 90 degrees. And it stays off until it comes all the way back around. Meanwhile, the ones that are on that start on the sides have to start at 0, and as the angle increases in one direction, say this one starts at 0 because it's to the side, and as the angle increases, as it becomes more vertical, it thrusts more. So my original solution was to find out the world orientation of the cube when it's at, align it to the world first, then use the pitch and roll angles, use the sine of the pitch and roll angles times the thrust needed, the magnitude of gravity, essentially, the total thrust needed to push the cube up. So thrust times the sine of the pitch angle, and then thrust times the sine of the roll angle, and then the negatives of both of those make up the pairs. But the top and bottom thrusters were an issue because the pitch and roll angles both affect, say that this is pitch and this is roll. Both angles will affect the bottom and top thrusters. And my initial solution only accounted for one of them, say pitch, or it might have been roll. And what would happen was that the cube would, jet off in one direction as it spun around. And in fact, the cube... Okay, it doesn't do it now, but so the cubes will generally begin to spin because of some small imprecision in the alignment of the thrusters. So I redid that, and instead of using the sine of the pitch and roll angles and the cosine of 1, I ended up using the dot product to come up with a cube that does this. I wish that the thrusters scaled so that you could see that each one is changing in magnitude. For instance, if the angle is just slightly off, these two look like they're on at full blast, but they're really not on very much at all. If you look at the input, it's like 7 versus this, which is at 52, 51. And it drifts just ever so gently downward, and then begins to spin because the thrusters are slightly off-center. Right now, I calculated just through trial and error, the approximate upward thrust needed to keep the thing afloat is 50, let's look at it's like 51.556 or something. Let's look in our code to do that. So, oh boy. Wiremod is excellent because it teaches us to break down problems into discrete steps. Literally teaches us programmatic thinking by taking a network of chips, like arithmetic chips, and linking them together. So this is a multiply, and you would take some values and funnel them in through many chips, which is an earlier solution had a series of chips for each part of the calculation for each thruster, so it made a really big mess. And Wiremod also features a chip called Expression 2, which is essentially if you understand how to program, it just effectively lets you cut down the number of entities that you're spawning into the game and program in this kind of interface. So the setup that I actually have here is this shouldn't be here. The chip takes an input of the entity that is, in this case, the cube that it'll be negotiating with, and it gets this through an entity linker, which is the one chip that I really needed to take out of the Expression 2. But I think that you can mark entities, or you can get entities just in Expression 2. Not sure how to do that yet, but so this marker says it allows the Expression 2 chip to be like, hey, what's that cube doing? And the marker's like, boop boop boop, it's rotated like this, or it's like straight up and down, etc. And then the Expression 2 chip processes this. I have it set to run on tick 3. What I originally thought that this meant was that it would run every 3 ticks. But I'm not sure if it is just like a boolean, like just a 1 or a 0, and I haven't dug deep enough to find out. The documentation for Expression 2 is really not extensive. So what I do in here is like EA is it's an alias for the entity, and what would happen if I didn't have either line 7 or 9 is that, I don't know if you can see this because of the solution. That's okay. That's alright. That's fine. So, okay, that's a little better. So, I had to assign the entity to another thing. This is part of me trying to figure out why, but what would happen was I would spawn in, I would link everything up together, and then the internal logic would stop responding to changes in the orientation of the cube. And so I just got it to update the entity object every time that this script ran. I'm pretty sure that I don't need the EA line, but I'll edit that later. So the Expression 2 chip takes an entity type and returns a bunch of other outputs. So it gives you the thrust for the top thruster, then the thrust for the bottom thruster, then the thrust for the thruster that responds to positive roll, then negative roll, then the one that responds to positive pitch, and then to negative pitch. And then for diagnosis, I had the roll and the pitch outputted too, so that I could like look at it in the debugger, which is on the left side of the screen. And I don't know if you can see that too well because it's tiny. And what I ended up changing this to was top, bottom, left, right, front, back, and I just have yet to rename my variables. So earlier I was talking about the dot product, and so I'll quickly show the equations that I used to think about this when I realized that the top could use the top and bottom thrusters could use the dot product instead of cosine of the angle, which is actually sort of what it is. Anyway, here let's check out those equations. All right, so this is the first equation. It says that the dot product of two vectors is equal to the cosine of the angle between them times the magnitude of each vector. Then the next equation is just a rearranging of that, where, oh, interesting. Okay, I just discovered I could do that. Where we divide the dot product of the two vectors by their magnitudes, and what this effectively amounts to is the cosine of the angle, in this case our pitch roll angle, added together, that's theta. Cosine of that angle is equal to the dot product of the two direction vectors, so two unit vectors. And we can rearrange those in our context like this. So the dot product of the front front vector and gravity, direction of gravity, is equal to the cosine of the angle between the front sorry, the forward facing thruster and gravity, and same thing for right and up. And then front is simply negated to get the back thruster, right is negated to get the left, and up is negated to get the down. So then in the code, which is in the game, and also probably really hard to see because of resolution, is exactly that. It's exactly that scaled by thrust. So each thruster, its magnitude is thrust times the dot product. And that is pretty much it, as far as I can tell. The specific thing about this solution that's not totally excellent yet is that it doesn't respond to changes in gravity. It assumes a constant gravity, which is a reasonable assumption to make given the game world. Given that the game world doesn't really change gravity all that often, it's not really something you want to consider. But that idea extends to that it expects a constant acceleration. So if you wanted to make a cube that hovered against other forces, like, for instance, if I unfreeze this thing and I knock it with the gravity gun, if we want to make a cube that responds to various other kinds of acceleration, what we would have to do is replace gravity with the total acceleration on the object, and then we would have to find a way to get the acceleration of the object by keeping track of its position in time, and then its change in position in time, and then its change in position over time. So its acceleration we would have to derive from keeping track of its position in many steps, which is not infeasible. And we do it all the time in, like, microcontrollers. I forget exactly what the acronym is, but I really dig it, and I was hoping to try and apply that concept to this. As for where to start on that, I'm just not sure. So real quick, I I'm gonna redo this. I'm just gonna do it all from scratch so that you can get an idea of how this works. And that way, I can take this stream and I can chop it up and make a tutorial for the process of making a hovering cube with 6 thrusters. A maximum of 3 of which are firing at a given time and a minimum of 1, and they scale in order to sum to the force necessary to counteract gravity. Yeah. So I've duped this. I believe I've duped this. I'm gonna dupe it one more time because, you know, stay sane. So I'm gonna give myself a nice little rope. This little breakable rope, and I'm going to constrain the two. Anytime you use advanced duplicator, it's important to constrain things that you want coupled, because wiring them together, as far as I can recall, is not enough. Although advanced dupe 2 lets you do areas. You do by area, but I don't know how to use it yet. It's new. So, I've got it duped. I'm going to save it as demo 3. No, we'll call it demo. I'm pretty sure. Whoa, oh, man, there's a grasshopper on my keyboard. That was alarming. Anyway, demo3.txt. Cube thing. Pretty sure it's already in there, but. Alright, and let's get rid of all of it. Alright. So let's start with a cube, and it's gonna be vertical. We'll figure out its orientation later. And so far, I'm just gonna start with 6 thrusters. We're gonna put 6 thrusters with 6 wire thrusters specifically with a force multiplier of 1 on each side of the cube. And we do the force multiplier of 1 because the thruster gets an input, which in our case will come from our expression 2 chip, and then it scales that thrust by that amount. So if it gets an input of 40, it'll output a thrust of 40. If the scale factor is 1, and 80 if it's 2, etc. So it is a multiplier. For a while, I just never understood why that, how that worked. It never clicked in my 8th grade mind, even though I was building helicopters in this fucking game, so. Anyway, let's see, what else can I do with this? Where do I go from here? Oh, it's pretty simple. We gotta set up our control board, which I always love doing. You know what, let's pick something a little bit more, let's pick something funny. How about a car? How about just the side of some vehicle? That's great. That's excellent. Okay. So this will make for an amusing visual joke here in a moment. Okay. Freeze the car so it doesn't go anywhere on us. And we're going to first link our cube to an entity marker, which detection, advanced entity marker. I think we just want the regular entity marker. But the advanced one has I've been using the advanced one this whole time. Anyway, this is the visual joke here, by the way, get ready for it. We've got a little alarm. Okay, yeah. Anyway, so then we right click on that, and then we right click on the cube, and now the entity marker is getting the cube's entity object from the game. So Garry's mod is yeah, this is the cube, and this is how you can talk with it. And we're alright, we're gonna make that shit float. Alright. Next, I'm pretty sure that I don't really have to do much of anything else. I'm just gonna make an expression 2 with a new... I wonder if there's a way to change the text size. Syntax colors, new tab, font size. Yes, we're gonna make it 25 so you can see all of this glorious code we're about to make. So, update our auto indent. Okay, I'm just looking through, showing myself. My hand also kind of hurts because my they're just on the ground. Sort of, I'm sitting on the floor in my back room because it's comfy. Editor, and it's sort of comfy. I guess my hands hurt, right? So it's not that comfy. Okay, I guess I can't make this any bolder. So we're just gonna leave it at that. All right, so we're gonna make ourselves a brand spanking new expression to chip. And we're gonna get an input, and we're gonna call that input E, and it's gonna be of type entity. So this colon means that the variable we're declaring E is of type entity. And we know that's what we want because the entity marker outputs an entity object. Unfortunately, the capitalization of these object types varies throughout the game. In expression 2, all of your variable names have to be capital. They have to start with a capital letter. They don't have to be fully capital, but they have to start with a capital letter. And types are always lowercase, which is basically the opposite of Java, if you've ever done Java. I like to use big capital, like single letters, just for objects that we're going to be using all the time, kind of like the global, the main, whatever it is. So that's fun. Outputs. Oh, hang on. I'm gonna message someone about this, about the fact that I'm doing this thing, because I think that he would enjoy it very much. Where am I? I don't know if you guys like weather report, but I've got bam. Okay. So I've got the DVR thing on, so you can rewind it. That's cool. All right, outputs. What are our outputs? They're the 6 thrusters. They're the 6 thrusters. We're gonna have a forward thruster. Okay, so a forward thruster, a back thruster, a right. Trying to determine how I want to abbreviate. A right thruster, a left thruster. I'm just gonna use capital R, capital L. Front, back, right, left, and I'm just spacing them so that they look like they're in pairs. I don't think that expression 2 is white space sensitive, so yeah. Okay, so right, left, and then top, front, back, right, left, up, down. Up, down. All right. By the way, whenever we... Okay, we're about to get there. So, here. We're gonna do some... I gotta relabel these. I gotta give them a different title because I'm about to use... Let's see. I'm gonna think about that for a moment. I'm going to run on tick. And I'm going to say 1. And that's going to make this update all the time. So I'm going to do some stuff with our FB, RL, U, and D. And the first thing that I'm going to do is I'm going to set F is equal to... Oh boy. How did I do this before? What do I have to do right now? I have to get the entity's orientation. Yeah, let's just look back at it. Let's look back at it. That's wrong. All of these are wrong. It might be even gone. That would be just great. Honestly, I wouldn't mind that too much. That's okay with me. Oh my god, did I just lose the one that I'm working on? I have not. Okay. So let's see. Our front is going to be our... What do we say it's going to be? Okay, we need a thrust variable, because I'm about to say the forward needs to be thrust. So thrust, I'm going to start with a value of 40. I know that that's higher than 32, which is what we were using for the cube before, but remember that with each thruster added to the cube, the thrust increases, and we didn't try it with 6 attached to it. So I'm going to say it's about 40. If I recall correctly, it's closer to 50. It's closer to 52 in the other script. So we're just going to start. In fact, I'm going to start with 50 instead. I don't care. So it's thrust times what? It's going to be thrust times the dot product of the entity's orientation and the world gravity. So I'm gonna start by setting the world gravity. We're gonna call it G, apt descriptor, and it's implied. E2 understands this to be we're declaring a variable. So G is equal to a new object of type vector. Vector is a function that returns a vector type, so it just implicitly sets G to the type vector. Vector 0, 0, -1. And so this will tell us that, here, I'm going to talk about this for a second, the XYZ convention, because I had to look this up before. Thrust times, we're just going to leave it G so that it'll save without break-in. So we're going to call this, what is this? Cube thing 3, because this is, 4, because this is like the 4th time I've done this. Okay, and it's saved, and we're going to upload it. It's wrong. Something I did was not correct. Thrust. Did I spell? Oh, thrust equals 50. Wow. I'm a genius. Okay, f of type number cannot be assigned value of type vector. What are we looking at? Ow! Okay. I know what's up with that. It's just... close the other stuff. Alright. Even in Garry's mod, I have trouble with having like a billion tabs open. I didn't even... So this is just incorrect. We're just going to say f is thrust for now. So what was I going to talk about? Oh, XYZ convention. It's really simple. This is really simple. Whenever you are looking at just a plane, like, where is it? General. We want a plane. So we're going to make a plane. Whenever you're looking at a plane in like math, you got your independent variable and you got your dependent variable. Your independent is your x, and your independent is y. And I think that we did a silly job by ingraining that so well into people's heads, because really what's going on is we got these two coordinates, x and y, that could be varying independently with another variable that's off of the screen. Like time, for instance, but that's okay. Maybe I just had a grasp of that really early, but I think that if somebody had, I don't know, I just think that's a lot more interesting because we're talking about games. Anyway, x and y are like this. X is left and right, y is vertical, but what happens when you put it in 3D? what happens when you put it in the game world. You could do it a couple different ways. For instance, like I think it's OpenGL, screen coordinates are X positive is right, Y positive is down, and Z is into or out of the screen. I believe it's out of the screen. But in Garry's mod, X and Y are like this. They represent coordinates on the flat world surface, which makes the most sense for a first-person shooter, where you're traveling around the world like this most of the time, and when you jump, you come back down. So then Z is our vertical direction, the direction that you jump in. Okay, is it safe to undo that? Yes. So, because if I undo too far, I'll just get rid of everything that we've worked for, which is really dangerous. I don't like that undo is Z instead of Control Z. There's no, it's not safe. It's really not safe. Anyway, so gravity is negative Z. Our jump is positive Z, and then we come back down towards 0, negative Z. Not really towards 0, towards the negative side of things. Towards negative infinity. Anyway, so thrust, where were we? Forward. Each of these, recall, each of our outputs is going to be expressed in terms of thrust and the dot product of our directional angle with gravity. So we want, I'm going to start by saying G, and then member function, member function, or what's the expression, like method? It's a member, it's a object, what the hell ever. So G has this thing it can do, and that is dot, because G is of type vector, so vectors have a dot operation, so that when you plug in another vector, in this case, our forward vector, it'll do that operation and it'll return a linear type, which we can scale with thrust, and then that'll be our F. So we want our entities, I think it's forward. Yep, it's forward. And then so this is a function that returns a vector, a unit vector in the direction of the cube's forward. To make our back, we're simply going to say that is F times -1. Expression 2 is really handy in that you can do what I just did by mixing types with multiplication. All I did was actually, no, that's not, wow, F is just a scalar, so that's, ignore me. But I did that earlier. I negated a vector with multiplication, and I was like, wow, that's pretty cool. I guess operator overloading is the expression. I wish we had that in Java. So then R, by extension, is going to be our or by, you know, whatever the, not extension, it's analogy is the expression. So by analogy, we're going to have our right, ease right vector. Then our left is going to be our right times -1. I like to be very explicit, so I put everything in parentheses. I'm not sure if this R times -1 works, but I just like to be explicit. So then our last one is going to be our up equals thrust times G dot, G's dot product with E's up vector. And then our down, the great finale is that our down is going to be U times -1, and I've made a typo. And assuming that I've done all of this in a consistent and accurate way, when I hit upload and exit, no errors. I like the sound of that. All right, so here's what we're gonna do. We're going to go debug and ooh, that makes me uncomfortable. I've done something wrong. All of our outputs are 0, which they should not be. Let me see if the thing is still linked. If not, I might actually have to do that thing that I said I didn't really have to do. So let's see. What's advanced editing marker? Right click, right. Ooh, it's already linked. Okay, let's see what happens if we turn it. Oh, E is null. Why is E null? Oh, we didn't wire the expression to... Our biggest mistake was that we never wired the expression to entity input to the output of our entity marker. Now everything is fixed. Our up is outputting -50 and our down should be outputting 50, which is correct. None of the thrusters are wired, but what this means is that down is firing, which means it's on the bottom, so we're gonna be like this. We're gonna say up is, or that one is down. Right, that looks correct. And our thrusters are not bi-directional, so when I do this and assign it to top, we should only get the one particle effect, and we do. Alright, that's cool. Now we're gonna say, we're gonna turn it on one side, and we're just gonna make sure up works. It does. So how do we know which one this one is? Well, it should be the one that's positive right now. I don't know if you can see, but in the debugger, which, let me see if I can make that bigger. Utilities. Options. Pew Pew is really cool. I might do something with that later. Other sound options, custom tool. Collabs. Yeah, I don't know if I can... Kind of a pain. Anyway, our debugger says that our back thruster is at +50. So what we're going to do is we're going to take this bottom thruster, and that's the one that should be all the way on, and we'll call it our back. Then the other one, by analogy, will be our front. Right? Front and back. So when I flip this over, our front works. All right, we've got a whole axis. We've got a whole axis of our cube working already. We're almost done. Now, we're going to take this thruster and point it down, and we're going to look at it, and it says, our debugger on the left side says that left is at 50. So left is our bottom one. Our bottom one will be assigned to our left output. And by analogy, the top one will be assigned to our right. And what should happen actually is now our cube will float, no matter what orientation it's in. It'll begin to spin, and it'll go down because our thrust is just a little bit too low. If I recall, it's something like 52.665. So we're gonna adjust that. 52.665, and I think that's gonna be off because I'm not sure what our ones place digit is. All right. Oh, it's a little too high. 51.556 or 665. I remember it was larger than 1/2, but less than 0.75. And there we go. We got it. We're exactly where we were before, which is just really cool. So this, of course, if you imagined that in real life you had the way to, if you had a way to get an object's acceleration, detect the force on it from gravity, and if you knew, like, if you had a wireframe cube with some fans in the middle that were capable of lifting it, you could basically do the same thing. Torque effects, I'm not sure. Like, you know, that would all come out in the wash, you know, because you'd be... But this is really the fundamental idea behind, like, making a hovering object, is figuring out which directions your thrusters are pointing in and dot producting them with the direction you want to go in, and then scaling it by how fast. And in this case, we end up with a cube that spins wildly. And maintains its vertical position. Oh, 6. No, it's just rotating. It's okay. Anyway, so force is a little low. Force is a little low. It's still not totally right. 6, 7, 5. That's pretty close. So, another logical step for this to go, another direction for this to go in, would be, say we have a slightly larger cube so that we can see it just a bit better. And we put thrusters, instead of in the center of the face, we put them around the edges. And you can see already that that's going to be, what, 6 times 4 is 24 thrusters, which is a lot more complicated than 6. But what this would give us the ability to do is to rotate the cube a specific way and then thrust in a particular direction. And I don't think we really need all of these for most applications, but like thinking in space, this is probably the most applicable. So what else can we do? What can we do now? I don't know, but I hope that this was... Alright, just... What else could I do with this? Okay, I'm gonna try that thing that I was talking about earlier. First, I'm gonna recap, and then we're gonna move on to something complicated, or a bit more complicated. So what did we start out by doing? We started out by creating a cube with 6 thrusters, 1 on each face in the center, approximately, with a scaling factor of 1. And then we linked the cube to a wire entity called an entity marker, which will say, like, look, here's the cube. And then that allows us to interface with a cube object in a programmatic way through expression 2, in which we took an input of our entity object and outputted the amount of thrust required for each thruster in order to stabilize the object. We figured out the magnitude of thrust specifically needed to keep the thing afloat. We assigned gravity a negative direction with no magnitude, but the magnitude is the thrust. Magnitude is the same thing as the thrust divided by the mass of the whole object. I believe that that's accurate because thrust is a force. Anyway, F. Okay, so and then we assigned the thrust value for each thruster to thrust times the dot product of the gravity direction and the entity's forward, right, and up direction. That is the direction of each thruster and gravity. That's pretty cool. And this solution is a lot more elegant than my original one, which... cube controller final. We're gonna call it final because that's good for me. What else can we angle thing? Like this is where I start. Like that. Okay, so look here just for a sample. Because I was trying to show you this earlier. These are debug. This is yaw, pitch, and roll, which I was getting from another chip. I wasn't giving an input of an entity. Thrust was 45 for some reason. I don't know why it was lower. Maybe I just hadn't gotten to a stable point yet. I think that's all. And I was using the sine of the angles and thrust, and that worked for a while, except that the bottom and top were always fucked up. And I made it a lot easier on myself by using the dot product instead. Okay, so now what I want to do is I'm gonna do a thing where I'm gonna go into our expression 2, and I'm going to keep track of the entity's acceleration by measuring changes in its velocity and then accumulating those over a time period. I don't know how to get the time between ticks yet, so we'll be looking up some things, but what we will see is that our entity object has a velocity vector inside of it because it's most efficient for the game to keep track of an object's velocity and position, and acceleration it calculates later. So our velocity is equal to our ease velocity vector, which this should be a return type of vector, and let's just make sure it works. It worked. Okay, v is our velocity. P is going to be position. I really like position, velocity, acceleration. Those are great ideas, but I really don't like that we use like like d, displacement, distance, something. We use in calculus we used s for distance. I think that's the stupidest idea on the planet. Or for displacement, I think it's awful. And just not intuitive. Anyway, so acceleration is going to be something that we'll find out later. And I'm just going to set it to 0 for right now, so that the game doesn't complain at me. So position is going to be probably pose. Yep. It's pose. Oh, you can't see, but these are tips that are popping up at the bottom. Position. What's the position of the input ranger? Position vector from a 4-coordinate reference frame matrix. Okay, anyway, our E position. And what is acceleration? It's the derivative of our velocity. But how do we get the derivative in velocity? Well, we need change in velocity over a change in time. And this will be in like discrete steps. I feel like it would be efficient to average it over like 3 or 4 ticks. So I'm gonna start with a value that we'll call dv, and oh, of course, that's a pain. Okay, anyway, capital D, capital V, equals, we're gonna set it to 0 for now, and then capital D, capital T, 0, just so that it will save. Load it, we store it, and hold on to it. Never lose it. Alright. Where are we going now? We're going to the web browser. We're going to our Steam overlay web browser, and we're going to look up expression to wiki. And we're going to go to the GitHub link, which is at the top. And we're going to go to, what are we looking for? What data type are we talking about? We're talking about, time. How do we get tick time? So tick exceeds the tick quota. Every tick the ops used minus the soft quota is added to a counter. Oh my god, that's great. It just in that paragraph they were saying, if your expression 2 is shutting down, get better at programming. Very helpful. Okay, so run untick. Guess you want to play with. Do we want to change it in terms of ticks, not in term? Change the velocity per tick. Honestly, that probably makes the most sense, but I don't know if a tick is 15 milliseconds. Tick click returns one of the real time, current time. Server start in seconds. Interval. Timer. Interval. Sets a 1 second. Accurate time. This is interesting. Unit per second. Tick interval. Tick interval. Time in seconds. That's perfect. So DT is going to be tick interval. Interval. Very good. And our change in velocity, in order to find that, we're gonna have to have a v new and a v old, and we're gonna subtract the new from the old, or rather, we're gonna subtract the old from the new through v new minus v old. Volt. Can I do underscores? Okay, anyway, that's good. I know it's counter to the convention that's in here. But that way. So I'm gonna stretch for a second. I'm gonna stand up. I'm gonna stretch my back. That feels good. Okay, so our change in velocity is our velocity new minus our velocity old. That's great. Our initial velocity is we're gonna get the e velocity. We're gonna get the e velocity, and then we're going to set v old at the beginning of each tick is going to be equal to v new, which is, you know, what it was before. So this is what will happen. We'll tick, and our v old will be set to v new, which oh boy, that's going to be a can of worms, because it's just going to be a can of worms, because what happens at the very beginning, we're given an uninitiated variable here, but we'll see what happens. Anyway, so v old equals v new equals e velocity. Oh no, what if we just do it afterwards? No, we can't do that. Then we'll go back to the end, and we'll come back around, and we'll get our v old is now our old v new. And then our v new will be updated with the enemy's velocity at a given time. I'm gonna just check and make sure that e acceleration isn't a function. It's not. It's not. that doesn't happen. So that's really good, because that means that this isn't all pointless. So how do we initiate persist inputs? Wait. Find out. Let's okay, I'm gonna look at the ats, because I believe that our answer is going to be hidden within the at signs at the top. Because what are persist variables? Persist. What is persist? If def, else, input or output. If def, entity set alpha number on the server, else, end if, equal, must proceed and input. Operate. Oh! Returns the current value of the variable minus the value of the variable at the end of the last execution. That's perfect. That's almost perfect. No, hold on. I have to pee really bad, so I can't do this. But you know what? Let's see if that's the answer. We're just gonna do stick a little one of those in. I can't. Hold on, I'll be right back. I'm gonna put up my little thing, my little coming back soon sign, and we're back. All right. How did we? Okay, v old is equal to v new is equal. Oh, what did I do? Screen. That one is the full screen. Are we broadcasting full screen? We are, and we've still got our equations if we need them. I'm gonna look at these for a second. We're gonna look at these and we're gonna think about what we're gonna remind ourselves what it is that we're trying to do right now. So, this is only the front right and up thrusters, but we also have a back left and down thruster to think about. So our thrust for each thruster is going to be each of these equations multiplied by the thrust. Since it's kind of difficult to find the cosine of the angle between our forward thruster and our gravity, so the direction of each gravity, hold on a second. It's kind of difficult to find the exact angle between each thruster's thrust direction, there we go, each potential thrust and gravity. So instead we use the dot product, which is just a little bit more elegant, and it's less stuff to keep track of, and it fills up less of the screen. But we assume that gravity is a constant here, which may not always be useful. For instance, consider that we might want the thing to thrust in a particular direction, or we might want it to respond to changes in things that hit it. So what I'm trying to do now in our present code is instead of g hat, it'll be g hat plus some other weighted directional quantity. So it'll be the direction of gravity plus some other force on the object, and we detect the force by figuring out its change in velocity over time, which brings us back full circle to where we are right now, which is this thing. I've done this before. I've done this before, and I have to establish a value for v new the very first time that the code runs, and with expression 2, I'm just not sure how to do that yet. I think that it's this persist operator thing. Syntax, trigger, there's a trigger directive, model, trigger, auto, loops, tutorials. I just don't know. Oh, you know what we could do? We could just check to make sure that it's not null. And then if it, so we're gonna use the not the Elvis operator, it's this guy. So null. I wonder what happens when null value. Okay, no. Null byte. What? Null terminated, null terminated, null terminated. Ish and init. Start with init. Oh. Variables. God, it's just, we don't know. Loops. Let's think about. I'm really just like calling out things. So here we're gonna just try something, and exists. Good for exists. Oh, T exists. Oh. Exists, blah, 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 blah. That's not what we're looking. persist. We're going to see what persist does. Parameter is not a number, then you just put that's it as in persist. I'm gonna say that I think that making a persist vnew. Oh, that might actually work because it'll say that vnew exists with some value. Oh god. Oh, we're trying to. Oh shit. Oh, that's old. Oh, kill me. Oh, okay, here it is. vnew, vold, vnew. It's new. It's a. Oh, it's got to be a vector. I think. Did it? Oh my god, we did it. Okay, so let's see. Our vnew is a vector. Our vold is going to be our vnew. Our vnew is the new velocity. dv as our vnew minus our vold, which is fabulous, and our dt is going to be our tick interval. So what we want is dv dt, dv divided by dt, which is going to be our a equal to acceleration is equal to dv dt. And yeah, that's pretty cool, am I right? And what I hope we'll see is that if our thrust is too high or too low, like if we use a lever or something on it, we could probably see like, I don't know, let's so I want to see it. I want an output from our expression too that will be the a as vector. A as vector. All right. Super cool. So it's 0. Ooh, oh my goodness. Look at that. And I bet that if our thrust is all kinds of fucked, let's see, we got an acceleration. Is it really accelerating that way? Like, spiking wildly. Maybe I should average that over a couple of ticks. In fact, I think that would be optimal. But we'll get there in a second. Alright, acceleration is 0. Velocity should also be 0. Oh, it spikes when it hits the thing. I love it. Between frames. Maybe this is okay then. Wow, this will be really interesting. So what I'm gonna do is, now that we have an acceleration, I'm just gonna take out gravity, and I'm gonna replace it with, I'm gonna straight up take out gravity and I'm gonna replace it with A. Ooh boy. Okay, so this is gonna be wrong because A is not a direction vector. It's what is it? It's just it's a full vector, so our dot product is going to be too high, and so our thrust is going to be crazy. And we'll probably see it jet off upwards. Whoa! Interesting. Wow, that's not what I was expecting at all. Okay, so we really actually do need to average this, but it is definitely resisting some changes. The thrust is too low. The thrust is definitely too low. Why is it too low? Because, oh, it's too high. A is really high. So how do we get the direction of A? Oh, thrust just needs to be taken out of the equation entirely because A is our acceleration. What we will need is like mass, maybe, but we'll get there later. Let's see what happens. Essentially the same thing, surprising no one. And there's still some gravity going on. This is kind of cool too because, oh wow, this is just fascinating. So there needs to be some like exponent stuff going on here. It really needs a longer interval. I'm surprised that the behavior is the same for that's so crazy. Love it. Okay, so we're gonna dt is gonna be 5 times the tick interval, and we're gonna make a persistent counter let's call it CT. And our counter is going to, if okay, how do we do? How do we syntax for each continue while I equals a assignment? I'm seeing assignment. I don't see comparison. Where's our comparison operator? I'm gonna try equals equals. That's standard-ish. If CT is actually no, I just get greater than or less than greater than if greater than or equal to 5. Our time period. Nope, if it's less than 5, we're going to CT++, which I believe you can do. I think I just saw that. C++. A++. Awesome. Assignment adding 1. Equals equals is the right one. For comparison, that is. Okay, so CT++. If CT is less than 5, we're going to increment upwards. So we'll start at 0, and once we hit 4, okay, so if CT, so else, CT equals 0. Can we do semicolons? Is that allowed? Wow. Okay, semicolon. Not allowed. Disallowed semicolons. I'm mad. Okay, so we got a persistent variable CT and a persistent variable v new. We can just call v new v for simplicity, and then v old will be the modified v minus v old delta v. So what we'll end up with is okay, ct++. All right, and so this will only happen every fifth thing. Oh, but that's wrong. I'm doing something wrong here. Oh, okay. Plus dv plus equals v minus v old. Very good. So what we're doing is every loop through we're adding, because we're going to average the change in velocity. So we're adding the changes in velocity. And then at the end of the loop, we're going to set ct as 0 and dv is going to be divided by 5. So that's our average change in velocity. dt is going to just be reassigned at the same time, and our acceleration is going to be set to dv dt. So our acceleration will update every 5 ticks. Believe that's what we're looking at here. And so what we should see is somewhat smoother behavior. Oh god, dv doesn't exist. Eric, which one is the most recent one? dv. I don't know why it does this. Evil to me. dv plus equals, okay, so dv just needs to be a persistent. As vector. What else are we doing? dt should be fine. Oh my god, it's working. Okay, so v as vector, dv as vector, a as vector, ct. So we're gonna, every 5 frames, so every frame we're gonna add our dv's together up until 5, and then we're gonna set dv is equal to itself divided by 5. dt is gonna be 5 times the tick interval, which has to be done because we need our 5s to cancel out. Do we need the 5s to cancel out? Yeah, because we get an average for 5 ticks. We'll see. I don't know if that's mathematically correct. I'm just... Yeah, no, I don't think that the 5 needs to be there. It's the same. It's the same 5. All right, so that's a little bit. That trims off one operation. So let's see what happens. Oh, wow, that's crazy. Look at that. Oh boy. I love how it just like peters out. Okay, so what is going on now? A is just really big. So we want... I think that what we want is A's direction. And how do we get that? We divide A divided by its own magnitude. A divided by U is A. Is it length? Left length. Ooh! Okay, and now we multiply it by thrust again. And then that way we can just change the thrust variable if it's off. But I think this should be about right. Because our thrust is our gravitational acceleration times our mass. So thrust will probably have to be set to the mass of the object instead of the 51.675 because that's already accounting for acceleration. Anyway, we'll see. Oh. Oh, wow. That's really exciting. What else can we do here? E to the power of K, like e to the power of CT. Or some... Why not E? I don't know. I should do that. Honest? No, it's not. It's not really going to. It's resisting changes in its velocity. Oh no, it's resisting. So I'm gonna add like an EK factor, and what that'll do is it'll scale this effect how do we, let's see if we can get math. Is that all? E. Of course. Euler's constant. Oh wow, that's convenient. So E to the power of, is that what it is? Exponentiation. I love expression. Okay, E to the power of K, which is going to be CT divided by, let's see, what factor should it be, like, CT K is 1 over, oh my goodness, there's a whole other layer here because we could go into jerk, which is really, this is what I'm adjusting right here, in an indirect way, as I'm adjusting the change in acceleration over time. I'm adjusting the thrust over time. Up to, it should be like 1 at the end of it, so CT over 5? Oh my god, what's e to the power of what equals 1, 0, so CT minus 5? What the hell is going on? I don't know, let's try it. Let's see what happens, because what we'll find is that this varies a little bit with time anyway. And hopefully this will give us a slightly, like, jostling cube. So it settles on the ground. Oh, no. No, we need it to do the opposite thing. We need it to start out really high and then get lower. I don't know about that. I don't know if that's a fact. Oh, 1 minus... What was I about to do? I was about to divide E... Oh, to the minus 1. Interesting, that's where that comes from. Wow, okay, I just... So e to the power of ct divided by 5 divided by e, so that's minus 1 in our exponent. Interesting. I don't know if that's... So how do we get to stop doing that? It's like when the acceleration is really low. Instead of using direction, it definitely should still be acceleration. And now that I've done this, we should see acceleration. So we're going to get rid of that. We're going to get rid of this line again. And thrust. I didn't even do anything with this E. I'm so embarrassed. Okay. All right. Well, that's intense. This 5 thing. Thrust equals 0 divided by 5 minus 1 negative 1 0 negative 1 e divided by e. So let's try that again. Oh. There's something else in here. I just don't know what it is yet. Oh, what if we... So I'm gonna rope this thing down, freeze it, and I'm gonna rope it. Square root of thrust. Okay, yeah. So the smaller the acceleration, the smaller the jerk. Oh my god. A times equals A length. Divided by 2, I feel like it should be. Because we just went from... Oh man, that's... So what did we do? We did A times A length divided by 2. A times equals A length divided by 2 times equals A times equals A length divided by 2. And thrust at 2 arbitrary number. Why did I pick that? Seems right. Thrust C a squared over 2 times the thrust. What happens? Ooh, that's villainy. That's where, like, what are they about? Okay, so I'm gonna maybe CT needs to be high instead, like the CT. 25 instead. Less than. CT. Okay. I don't know if this is gonna help me. Maybe interval device. As CT approaches the interval, come closer to 1, but it starts out at 0. Ooh, that made things a lot more intense. What did I do? What did I change? Oh, the boy. Maybe he needs to be shorter. It needs to be smaller. CT over interval will go from being a fraction. Ideally, it'll start from 0. Maybe this like complicated version is last time. I set thrust equal to 51. 52 is going to be too high. It just needs to respond a bit more slowly. I don't know how to do that. The E expression still seems improving things, though. A needs to be so if the A is multiplied by itself, Right now I'm just throwing stuff out there. That is a lot better. Overall slow motion. But not necessarily when it's going to the side. And not enough to completely counteract gravity. Why is that? Oh my god, the cube is 8. Each of those things are 1. What's 8 plus 6 is 14. It's not even a little bit better. Acceleration is going up over time, which it needs to not be doing. That 30, is that the span of 30 frames? That's 30 frames. It does not need to be multiplied by thrust. Because it's not getting So we don't do this. We definitely don't do that. Boy. Alright, so our acceleration is like constant. Maybe we need different intervals. Maybe we need maybe the interval should have something to do with the magnitude of the acceleration. That's a lot. I guess this is actually the best that it really can be, because time in this video game is unfortunately just not continuous. velocity. Can we do that? Can we use divided by velocity? dvdt. Alright, I think we're gonna give it another 10 minutes and then I'll call it. In some capacity, have achieved. If I go back just a little bit. Get rid of this. And that's right. I feel like maybe there's something to do with because the longer it spends moving in one direction, the less thrust we want. Say Let's see if that helps. Oh, yeah. Yes. Um. Oh my god, e to the power of e velocity, where if e velocity. Anyway. Oh my god. Oh. You're bogus. Two. Oh. Thanks. So, as velocity increases, A should also increase. So this should be it's gotta. Well, let's see what happens if I do it each way. Motion 39, 139. Oh, yeah. Oh, wow. Derek, I need your help. Critically damped. This is the problem. Critically damped. We have an oscillating system that is just not... It needs to have a coefficient of E something. It has to have a factor E. Actual damping over critical damping. Where is that? dx dt, the velocity. Wow, okay, well... How do you critically damp something? Well, it doesn't have to be minimal, it can be under damp. So... Velocity is integral pixel. System. Oh, okay, so if our acceleration, which is our change in acceleration just 0.25. Rest is 1. Well, okay, so, because I guess what's happening here is that it's resisting changes in its motion, meaning that it'll fall more slowly. but it's getting these really erratic sideways motions that are coming from where? What happens if I do the thing? Really reduce. Oh, wow. Oh, wow. Okay. Velocity. Riser. Damn. Okay, I'm going about something here wrong. plus equals a old divide a by the don't need I don't think so. So we're failing to give a good value. A equals dv dt. Interesting. Alright. So we're also going to average duration over time. So A is going to be dv over dt. So yeah. Hmm. Oh my god. Yeah. I need every I think no. Plus equals b minus. That's gonna be. We're gonna have a long. Our thrust on a. Huh. go back. Get rid. Bit of acceleration. So that all? That's all. That's all I had to do. Well. This is kind of... Oh, should be 2. B plus it. And gravity enough. Ooh, yeah. Yep. 30. Incredible. Almost. Ooh, wow. Alright, so with a little bit of extra effort and really a mistake on my part, we have arrived now at, oh my god. We've arrived at a cube that we can shoot at with all of the weapons at our disposal, and it will do its very best to stay right where it is. It'll take some impulses like explosions, it'll react to them, but it won't. Oh, God. Alright. Alright. I think that's a good place to end the stream.